Hi friends. So today we will be starting in our senior intermediate, that is very interesting chapter, magnetism and matter. Okay, it's a small chapter, magnetism and matter. Magnetism and matter. This is sixth chapter. It is a small chapter. So from this we will be getting 2 marks from MSET. We are getting 2 marks in MSET. So first of all, in this chapter, let us see various important points regarding magnet. Okay, so we know bar magnet. Okay, generally in the case of bar magnet, for all cases we will be taking the length as 2L, length of the magnet. Okay, but here one point you have to make a note. This distance is called as geometric length. This end to end, this is called as geometric length, GL. Okay, this is called as geometric length of the magnet. And as we know, the poles are little inside, north and south poles. So this is called as magnetic length. So generally magnetic length is taken as 2L. Okay, generally the magnetic length is taken as 2L. ML is equal to magnetic length. But what it was observed is, for example, say geometric length is 100 centimeters, magnetic length is considered as 0.4 cms, I mean 84 centimeters, please, 84 centimeters. So that means, what is the condition here? That means the magnetic length of the magnet is generally 0.84 times geometric length. This point you have to make a note in the examination. They are asking regularly. అంటే అర్థం ఏంటి, ఒకవేళ జామెట్రిక్ లెంత్ 100 సెంటీమీటర్లు ఉంటే 100 సెంటీమీటర్స్, వాట్ ఈస్ మ్యాగ్నెటిక్ లెంత్ 84 సెంటీమీటర్స్. 16 centimeters hardly it will be difference. Okay, because poles are little inside. Okay, so therefore the magnetic length is equal to 0.484 times geometric length. That means what happens, you can see, you can check it, 0.84 times geometric length. Geometric length ఎంత అనుకున్నాం, 100 centimeters. So into 100 if you multiply, what happens, 840012, so 84 centimeters. So magnetic length is 84 centimeters. Please make a note of this one, because this is the concept given by the scientists. Okay, and in all cases we will be taking the length of the magnet, bar magnet, as 2L. Okay, and the geometric length is slightly greater than the magnetic length. Clear? Okay, next we'll go to the next item. Okay, so this chapter you can consider as a revision chapter, because already in electrostatics 4th chapter we discussed about various laws in electrostatics theories, Gauss laws, okay, and also an axial line, equatorial line. All those again we will be revising in this chapter. Okay, so that's why I am telling this chapter is very small one and is a revision chapter. Okay, so let us start with this one. What is pole strength? Generally in a magnet, this is the bar magnet, these are the poles, north and south, and this is the length of the magnet. So generally pole strength is indicated with a letter small m. Pole strength anedi, it is indicated with a letter small m. There in electrostatics you will be calling as charge, plus q minus q. There isolated charges will be existing, ante plus minus q ఉంటాయి. ఇక్కడ monopoles does not exist, only plus ఏ ఉంటుంది, plus m, plus m minus m ఉండదు ఇక్కడ. ఓకేనా? So those are the things you have to understand. So what is this pole strength? This is indicated with the letter m. Pole strength means with whatever force it is attracting the magnetic particles or repelling, that is called as pole strength. And units, SI units are generally ampere into meter. This is the SI unit of pole strength. Pole strength and enti, when you put the magnet before any magnetic materials, it will attract or it may repel depending upon the polarity. Okay, so the SI unit is ampere meter. Next, magnetic dipole. Magnetic, దీని జనరల్గా magnetic moment అంటాం, or it is also called as magnetic dipole moment. Magnetic dipole moment. Same term again you will be heard in the last chapter, that is electrical dipole moment. So here magnetic dipole moment is indicated with the letter capital M, it is a vector. So therefore vector, it is given by length of the magnet into pole strength. This definition em cheppochu, it is the product of length of the magnet into pole strength. So what are the units? Length pole strength ampere meter into meter, that is ampere into meter square. Ampere meter square. So the definition of magnetic moment is nothing but product of pole strength into length of the magnet. Units ampere into meter square. Formula, it's a vector. Okay. And make a note the direction, as I told you in charges. In charges it is plus q to minus q to plus q. The dipole moment, it is from minus q to plus q. Here minus q will be acting as a south. In general, minus q is acting as a south pole here, negative charge. So what happens? Field lines will go from externally north to south, but moment is given from south to north. Magnetic moment is given from, suppose this south pole is north pole. So this is how the magnetic moment it is given, direction. Magnetic moment direction is given from south to north pole, please. Direction. Okay. See, as I said just now, it is a revision chapter. What all you have learned in the electrostatics, same thing will be again revising, please. Only the terminology will be different. Clear? So magnetic dipole moment, you have observed what are the units and also the definition. Now let us learn some more points. For example, same magnetic moment, if you take a current carrying loop, suppose this is a loop carrying current, circular loop carrying a current I. For this also, magnetic moment, how you have given? I into A. Okay? Magnetic moment is given by I into A. This I means strength of current, amperes, area, meter square. So magnetic moment in a current carrying loop formula, moment M is given by, okay, I into A. Strength of current, amperes into area, meter square. Same unit again you can see, ampere into meter square. Clear? Right. Now, let us go further in this chapter. Now, as I said just now, the magnet moment. For example, I'll give some diagrams for you. For example, this is a bar magnet. For example, say this is south, north. So you can see magnetic moment. Okay. Again south, north, magnetic moment. The angle between them is 90 degrees. For example, two bar magnets having same magnetic moment, M and M. You can see the moment direction is here, this from south to north. So what is the resultant of this one? Resultant can be used by using parallelogram law. That is A square plus B square plus 2AB cos 90. This will go cancel because cos 90 is 0. So what is the value? Root M square plus M square, 2M square. That is root 2 into M. So if two bar magnets are perpendicular to each other, making an angle 90, the value is root 2M. Okay? You can change the figure direction also. Okay? For example here, south to north. Okay? You can change the direction, you can understand the things. Suppose same bar magnet moment M, this is south to north. For example, south is kept here, north. Now the moment will be in this direction. Now you can see one is acting in this direction, another moment is in this direction. So what is the net magnetic moment? M1 minus M2. So M net in this case is equal to M minus M, that is equal to 0. So in this case, because in the opposite poles are in opposite direction, and as I said, the magnetic moment always from south to north, just like an electric charge is minus Q to plus Q. So in this case, net magnetic moment is 0. Let us see the next case. For example, These are the poles. Okay, magnetic moment. For example, another magnet is kept in this fashion. Okay, south and north moment. Now you can see here the moments are making, for example, say some 60 degrees. So what will be the resultant for this one? Again your parallelogram law, root over a square plus b square plus 2ab cos 60 degrees. And you know, since cos 60 is equal to half, so what happens? Root over m square plus m square, that is 2m square plus 2 into, again here m square into half cos 60. So here m square, 2m square, that is 3m square. Root over 3m square, that is root 3 into m. So this is the value. So like this you can find the resultant magnetic moment in different cases, okay, according to the concept. These points are very, very important regarding MSET and NEET examinations. Okay, so but that's why I'm telling, concept is very, very important. If you know the concept, you can understand and try to do any problem given in the examination. Okay, and one more thing I want to tell you, very, very important thing. What happens to the bar magnet? For example, it is cut horizontally. This is the bar magnet. Two cases I'll try to explain. When it is cut perpendicularly, exactly, okay, as I said, the length is 2L. Length of the magnet is 2L. When it is cut horizontally, x dash, and when it is cut vertically, what happens? This is the original length. So please make a note, when the bar magnet is cut horizontally, then what happens? Length remains same. There is no change in length. There is no change in length. The pole strength becomes half, m by 2. Pole strength becomes half. Here initially the pole strength was m. So length remains same. Pole strength becomes half. Whereas in second case, if you observe, length becomes half. Okay? When it is cut perpendicular, length becomes half. But pole strength remains same. No change in pole strength. Okay? So when a bar magnet is cut perpendicularly, exactly center, length becomes half, pole strength remains same. But here, pole strength becomes half, and length remains same. Now same magnet, for example, it is bent into semicircle. Same magnet, if it is bent into semicircle of radius r, okay? Same magnet, if it is bent into radius r. So this is the length of the magnet originally, 2L. This was the magnet, isn't it? Initially the magnet was like this, bar magnet. Okay, south to north. Initially what was the length? 2L. So this magnet is some benches of semicircle. Now what happened to the length? This length of the magnet has become equal to what? Perimeter. Half of the perimeter, 2 pi r. That means 2L by pi is equal to r. This length of the magnet has become equal to the semicircle. How much length? Half perimeter. Now we know already what is magnetic moment formula, 2L into m. Okay. Now because of this bending, what is the new length now? This is the distance now. So what will be now? I'll take it as capital R, because here we are using capital R. Okay. అక్కడ క్యాపిటల్ ఆర్ తీసుకున్నాం కాబట్టి క్యాపిటల్ ఆర్ తీసుకుందాం. డోంట్ చేంజ్ ఇట్. ఓకే, పుట్ ఇట్ ఎస్ క్యాపిటల్ ఆర్. So here what happens now? What is the length of the magnet? Now the length of the magnet is become as 2rm. 2rm. Okay na? And what is here r now already? 2l by pi. So 2 into what is r? 2l by pi into m. This is the new magnetic moment now. But we know what is 2lm, magnetic, the initial magnetic moment. So 2m by pi. So this is the magnetic moment of the bar magnet when it is bent into a semicircle. Please note down, this concept is very, very important regarding magnets. Okay, when it is bent into a semicircle, the new magnetic moment becomes 2m by pi, where pi is 22 by 7 or 3.14. M is the original magnetic moment before bending into semicircle. Clear? Right. Now suppose if the same magnet is bent into an arc of a circle, what happens? We'll see. ఓకే, అదే మ్యాగ్నెట్ని మనం ఒక ఆర్క్ ఆఫ్ ఎ సర్కిల్గా బెండ్ చేస్తే ఏమవుతుంది? సో ఆల్ బై యూజింగ్ మ్యాథమెటికల్ థింగ్స్ యూ కెన్ సాల్వ్ దిస్ వన్. సపోజ్ this is a bar magnet of length 2L. Okay, now suppose this is bent into arc of a circle. You can see now this has become 2L length. Arc of a circle it is bent. Suppose this is the angle theta. Now what happens? The magnet, this will be the new distance. Okay, okay, this will be theta by 2 bisector. This will be theta by 2. So you can see when it is bent in this fashion, new magnetic moment is given by 2m sine theta by 2 by theta. This is the formula when a magnet is bent into arc of a circle. Okay, this is 90 degrees. Okay, theta by 2, theta by 2. So this is the formula you have to remember. 2m, m is original magnetic moment. Here theta is in degrees and here theta is in radians, please. Here theta is in radians, this is in degrees. We'll check one problem. For example, theta is equal to 60 degrees icharu. Assume 60 degrees. So m dash is equal to 2m sine 60 by 2 by theta in radians. So radians ఎలా మార్చొచ్చేది మీకు తెలుసు కదా, ఆల్రెడీ I told you before. 360 degree is equal to 2 pi radians. 1 degree is equal to 2 pi by 360 radians. That is pi by 180 radians. 60 degrees is equal to how many? So pi by 180 into 60. 60 ones are 60. So pi by 3. So here theta is radians lo pettamanu kabatti pi by 3. So here how much? 230s. That is equal to 2m. What is sin 30? Half. Okay, into 1 by 2 by pi by 3. 3 will go to the top. So 2 gets cancelled. What is the answer? 3m by pi. So in this case, when 60 degrees angle is given between the radius of the circle, this is the radius. So what is the answer? 3m by pi. Okay, na pakkan radha 3 ikkada. So answer is what? 3m by pi. So in this case, if you change the angles, you can use this direct formula. 3m by pi. 3m by pi, please. Adotna? So very easily you can solve these type of problems. Just use this formula when it is bent into arc of a circle. 2m sine theta by 2 by theta. This theta is in degrees, this is in radians, please. Clear? Please note down. Now let us go to the next one. Next one is, see how the magnetic field lines will be there. How the magnetic field lines. See, already I told you in electricity, that is electrostatics, there how the field lines are coming. From positive charge, field is going away, to negative charge, field is coming. In the same way here, what happens? For example, if you take any bar magnet, these are the poles. Always externally from north to south, the field lines will be going. Okay, they are meeting at south. You can see north to south. Okay, the field lines will be going from north to south. And inside I told you magnetic moment from south to north. Okay, so the lines will be going in this fashion. From north pole going away. Okay, and south, as I said, they are coming towards the south. These are the magnetic field lines. Okay, so from north to south, it is meeting at south. From north it is going away. And please make a note, no two lines, magnetic lines. For example, if you take any two lines, No two lines, any two lines, air and lines could meet over. These are the properties. Just like in electrostatics, how I told you, same property, because if you draw tangent at any point, you will get the magnetic field direction. If you draw tangent at any point, you will get the magnetic field direction. You can draw, see, B1, B2, B1, B2. If you draw tangent at any point, you will get the direction of magnetic field. So what happens when the two lines are touching? The resultant will be in two directions, which is highly impossible. So that is why no two magnetic lines or no two electric lines will meet each other. If they meet each other, you can see, if you draw tangent there, you are getting the magnetic field direction. One is in that direction, another is in this direction. So two resultants are getting, which is highly impossible. Okay? So that is why no two lines will be meeting each other. These are the properties. I don't want to repeat because already in electrostatics, what all properties I told you, same thing will be repeating. I told you it is a revision chapter. Revision chapter. We will be revising the chapter electrostatics in this one. Okay? Now let us go to the next one in this magnetism matter. Now what I will do is, we will compare the things. As I told you just now, it is a revision one. We will compare. Okay? In electrostatics, what we have learnt, now magnetism. Same thing will be repeating with the terms different. So I told you in electrostatics, in electrical dipole, minus q plus q, dipole moment is given by P bar, and it is nothing but 2A or 2L. Somebody will take 2A, you can also take 2L. Some authors are also following 2L. So electrical dipole moment is given by 2A into Q. And what are the units? Charge coulomb, distance meter. So this is the SI unit. Now coming to magnetism. In magnetism, you see the bar magnet, south and north. So this is the magnetic moment direction. Length is taken as 2L. So magnetic moment vector, same like here, it is given by length of the magnet into pole strength. SI unit, ampere into meter square. Clear? So here I am telling you, it's a revision chapter. Everything whatever you have learned again, you will be revising, please. Okay? Right. Now this is regarding electrical dipole moment and here magnetic dipole moment. You can see the changes here, the terms and terminology. Okay? Right. Now second one, there already you have learned axial line. Axial line, that is at a point P, distance D or R, D or R, and this will be A, and this point will be R minus A, and this is R plus A. So in this case, for short dipole in axial line, what you have learned? Electric field intensity is given by what? This direction. 2K constant into P by R cube, where P is the electrical dipole moment. K is constant. K is equal to 1 by 4 pi epsilon naught, which is equal to 9 into 10 power 9. This entire value 1 by 4 pi is equal to 9 into 10 power 9 Newton meter square per Coulomb square. Here on the axial line. Same thing for magnet. If you take on the axial line point at a distance D or R, okay, you can say D or R. Here length becomes LL, D minus L or R minus L, anything, and either తీసుకుంటాం D కానీ R కానీ ఇక్కడ D plus L, ఎక్కువగా D తీసుకుంటాం. So in this case, what is the magnetic field induction? Vector B bar is equal to 2K M, in the place of P dipole, here M, by R cube or D cube, but either తీసుకోవచ్చు, R cube or D cube. Here K constant is equal to mu naught by 4 pi, and you know 4 pi is constant, mu naught value కూడా తెలుసు మనకి, 4 pi into 10 power minus 7 Henry per meter. So you can see the letters, the literature here. Here P vector M vector, magnetic moment, dipole moment, electrical dipole moment. Distance d or r you can take, axial line. In the same way, please make a note, this is for short dipole. Long already you have given that equation d square minus l square whole square. Here d square minus l square whole square or r square minus a square whole square for long one. Okay, let us not discuss here long, let us take for the short one. In the same way, equatorial line, same way you have taken for equatorial line. So this is total distance 2a. Equatorial means the point is here lying. Its distance d or r. D or r. So you have made one triangle here. You can see from positive. Okay, this is one force E1, negative to positive attraction. Okay, again positive to positive. Point kada 1 ampere meter తీసుకున్నాం. 1 ampere meter, what you have taken charge here, 1 coulomb. What is the unit of charge? Coulomb kada. So ఇది ఇక్కడ ఏమవుతుంది? You can see here what happens is ఇక్కడ point 1 point unit charge తీసుకున్నాం. Unit charge. So unit charge ఈ రెండు ఏమవుతాయి, డైరెక్షన్ ఇలా వెళ్తుంది ఒకటి. ఓకే, ఇంకోటి ఇలా వెళ్తుంది. Resultant will be here. See, I told you from positive charge, positive there will be repulsion. Okay, రెండు నెగిటివ్ అనే repulsion. పాజిటివ్ నెగిటివ్ ఏమవుతుంది, అట్రాక్షన్ అవుతుంది. ఓకే, పాజిటివ్ నెగిటివ్. సపోజ్ ఇక్కడ నెగిటివ్ తీసి ఇక్కడ పాజిటివ్ తీసుకుంటే అట్రాక్షన్ ఇట్ విల్ గో ఇన్ దిస్ డైరెక్షన్. It will go in this direction. Okay, so please make a note. So in this case, what you have written for short dipole, I am giving the directly value. Short dipole, E is given by in this direction, negative x direction. That is minus k p vector by r cube. For short dipole, again same, k is constant here. Why minus here? Negative direction of x. That is minus I cap. Minus I cap. Here positive x direction. Okay. In the same way, here also you got what is b vector, equatorial line, same k into minus k into m cap by r cube. Again negative in this direction, opposite direction of x axis. So here malli k, same thing, mu naught by 4 pi. Okay na? So in రెండింటికి difference చూడండి 2 times. You can see here axial line, E on axial line is equal to what? 2 times of E on equatorial line. You can see this value is equatorial line. Okay, this is what axial line into 2 into this value is equatorial line if you take magnitude. So on axial line the field, electric field is 2 times on equatorial line. ఇక్కడ కూడా అంతే, axial line, magnetic field on axial line you can see 2 times. What is this value? Equatorial line, B equatorial. So same things are repeating here for as a revision. అర్థమవుతున్న formulas? Right. Please note down. Clear? Right. Now let us go some more terms. Those also will revise. And there also I have given one more formula for at any angle. Okay, at any angle కూడా ఇచ్చాను మీకు, అది కూడా రాసేద్దాం. In this one, in electrostatics as well as magnetism, at any angle. See there I have given one formula, excellent formula for you at any angle. Please make a note. See, in electrostatics and magnetism at any angle, and for example I told you minus q plus q at somewhere point here p. Okay, some angle theta. Okay, this is the magnetic moment direction vector. This is p cos theta, and this is component p sin theta. So this is axial line, this is equatorial line. So if this is the case, I have given one formula for you. E is given by k p by r cube into root over 1 plus 3 cos square theta. In the same way you can apply here also. Okay, same way you can apply here also if any angle is given. ఇక్కడ చూడండి, if you apply an axial line theta, ఇక్కడ కూడా same thing, k p by r cube into root over 1 plus 3. We'll do one thing. See, in this case, even though you take the formula or you don't take the formula, it's okay, because I am giving in general case. In general case, I am telling you. Okay na? General case lo meeku ee formula enduku cheptunanante 3 cos square theta. Why I am telling in general case is, see, Kp bar, I mean, ikkada Kp bar badalu magnetic moment vastundi. Why I am telling in general cases, please make a note. For example, suddenly ask on axial line, what is the formula for short? Axial, what is theta? 0 degrees. Axial line. Axial line, dipole moment and point, into same direction. Theta is equal to what is cos 0? 1. This gets cancelled. So 3 into 1, 3 plus 1, 4. What is square root of 4? 2. 2 Kp by r cube. Equatorial line. Theta is equal to 90, you can see, making angle 90 degrees. Cos 90 is 0. Root 1, 1. Okay? Of course, it is negative direction, you can take minus Kp by r cube. Same equation in the axial line. Theta is equal to, అంటే ఇక్కడ సౌత్ పోల్ నార్త్ పోల్ ఉన్నాయి కదా పోల్స్, ఆ రెండు యాక్సియల్ లైన్ ఎలా ఉన్నాయి? 0 degrees. Cos 0 again 1. Square root of 4 2. 2 Km by r cube. In the same way, equatorial line theta is equal to 90 degrees. Cos 90 is 0 again. You will get minus Km by r cube. So this is generalized formula I have given electrostatic. That also you can apply here at any angle if it is given. Okay? That is Kp by r cube root over 1 plus 3 cos square theta, or Km by r cube in root over 1 plus 3 cos square theta. You can apply both. Okay? So these are the comparisons regarding electrostatics and magnetism. Various formulas, various axial line, equatorial line. 2 more are left out, that also we'll discuss. That is, in electrostatics, we have seen this is the field direction. In field direction, and this is minus q, this is plus q, 2a distance. If it is making an angle theta with the field, okay, so there what you are saying, this is the force acting again Eq, and this is the force acting again minus Eq. So what is the torque acting here? Torque is equal to force into perpendicular distance. There you discuss what? Force into perpendicular distance is 2a sin theta here. And where 2aq is equal to p, therefore EP sin theta. Okay? So here torque ante in electrostatics we got P cross E. Same thing here also you can apply in magnetism. If this is magnetic field and suppose this is a bar magnet, south and north, let this is the angle. So force acting is equal to MB in this direction. Hi friends, sorry for interruption, little power cut. So let us continue the chapter. See, I am comparing regarding electrostatics and magnetism. Okay? Now you see in this electrical field when is there, you can see what is the torque acting here? P cross E, that is PE sin theta. In the same way in magnetism, if you see, suppose this is the magnetic field here. Okay? So here what happens, force will be acting in that direction and the force will be in this, and finally torque will try to keep it in the field direction. So here also what you are having, a magnetic field, that is force acting, is given by MB sin theta. What is torque actually? What is torque? Torque is equal to force into perpendicular distance kada. Torque is force into perpendicular distance. Force into MB into perpendicular 2L sin theta. And what is 2LM? Capital M. Therefore in this case, MB sin theta is the formula, or torque is equal to M vector cross B vector. Here you can see P cross E in the place of P, M, E in the place B. So these are the comparison values for torque. In the same way, if you go to the next one, potential energy. Electrostatic potential energy lo మనం ఏం చూసాం, minus P dot E vectors you can see. Minus, ఇది ఎలా వచ్చింది? I told you there that day integrating this equation. If you integrate PE sin theta within the limits theta 1 to theta 2, integral of sin theta is minus cos theta. Therefore, theta 1 to theta 2 upper limit minus lower limit. So I am not showing the derivation, just I am telling. So here electrostatic minus P dot E, here enti potential energy. In this case magnetism low. In the case of magnetism, potential energy formula enti, see same, minus P place low M dot B. Okay. So finally చూసుకుంటే ఎలా అవుతుంది, minus MB cos theta, because the direction you can see, the direction of the electrical dipole and E, if you take theta is equal to 0 degrees, same direction తీసుకుంటే అయితే ఏమవుతుంది మనకి cos 0 1. ఓకేనా, ఒకవేళ 0 అయితే otherwise you can put angle here. So this is generalized formula, potential energy minus MB cos theta, here also minus PE cos theta. Okay, suppose he may ask you what is the work done in rotating from theta 1 to theta 2, then you can apply here. Next case, work done in rotating the dipole from theta 1 to theta 2, then what happens, you can apply directly formula or PE cos theta 1, that is U final. The general formula ఏంటంటే ఇక్కడ, I'll write it here, general formula U final, work done is given by potential energy final minus potential energy initial is equal to work done. So U final అంటే ఏంటి, rotating from theta 1 to theta 2 అంటే minus PE cos theta 2 minus PE cos theta 1. So finally ఇది ఏమవుతుంది అప్పుడు ఇక్కడ చూడండి, I'll write it here, minus PE cos theta 2, minus into minus plus here, plus PE cos theta 1. If you take common PE, inside ఏమవుతుంది, cos theta 1 minus cos theta 2. This formula you can use final as work done in rotating from theta 1 to theta 2. Either you can use minus PE cos theta or U final minus U initial final formula. PE into cos, the same thing here you can apply. That is MB into cos, same thing here. MB magnetic moment into B cos theta 1 minus cos theta 2. This is the work done in rotating the bar magnet from initial to final position. So U final, ఇక్కడ కూడా ఏంటి work done? Work done is potential energy final minus potential energy initial. You can apply cos of theta 2 minus MB cos theta 1. U final minus U initial. Final angle minus initial angle. So these are the comparisons you can see work done. Here PE into cos theta 1 minus theta 2. Here MB into cos theta 1 minus cos theta 2. Clear? So these formulas are very important in doing numericals. Clear? Right, very good. So these are the comparisons I told you in the beginning only. It's a revision chapter between electrostatics and magnetism and matter. Most of the thing. Small chapter, easy chapter, and also scoring. I'll give a small example. For example, I'll give a small. Suppose theta 1 is equal to 0 degrees. Theta 2 is equal to 180 degrees. So what will be the work done? So work done direct form you can apply. Electrostatics kabatti MB PE, or in magnetism work done in rotating is equal to original formula minus MB cos theta, or what is the direct formula, MB into cos of theta 1 minus cos theta 2. అదే కదా చూడండి కావాలంటే minus MB U final minus U initial is equal to work done. So MB cos theta 2 final minus MB cos theta 1 plus అయిపోతుంది, ఇక్కడ కామన్ తీసుకుంటే theta 1 minus theta 2. So finally what will be the answer, MB cos theta 1 0 degrees cos 0 minus cos theta 2 180 degrees, that is 180 degrees. Cos theta 1 minus cos theta 2. So finally ఏమవుతుంది, MB into cos 0 1 minus cos 180 minus 1. So MB into 1 minus into minus plus, that is 2 into MB. So this is how you have to solve the work done in rotating the bar magnet from initial to final. If any angle is given, don't apply this one directly, you can apply this formula. solid one, mb into cos theta 1 minus 2. Here also pe into cos theta 1 minus cos theta 2. Clear? So these are the comparisons. Please make a note. Very important formulas these you have to apply. Okay? And one more last comparison in this case left over, that is for example here you can see this is the field direction. In electrostatics I have given minus q plus q, this is dipole, okay, making some angle. Suppose it will try to bend in this direction. It will put in this direction minus q plus q. For example, small movement is made for this one. So what happens? It will be making small oscillations, SHM. So what is the time period in this case? Time period will 2 pi into root over I by P E. I by P, where P is electrical dipole moment, E is electric field. This is the field direction. Okay? And what is I here? Moment of inertia. I is moment of inertia of this one. I is equal to moment of inertia. P. What is P here? Electrical dipole, 2AQ. P is equal to 2AQ. And E field 2 pi is constant, T is the time period. In the same thing, here also you can apply in magnetism. So in the same case, in magnetism, when the bar magnet is kept, okay, for example, this is initial position, south to north, small tilt is done. For example, it is making simple harmonics like this. It is making simple harmonic motion. So what is the time period of the bar magnet? 2 pi into root over I by, in the place of P, M, in the place of E, B. But here B I'll write as BH. What is BH here? Earth's horizontal magnetic field. What is BH here? BH is called as Earth's horizontal magnetic field. Because vertical field is considered very little in this case. Maximum Earth's horizontal field is taken. Okay? So I again moment of inertia of the rod about the axis, that is given by, about the axis I told you in first year, ml square by 12. About the axis passing the center. Okay? So it is given by ml square, mass of the rod into length by 12. BH value anyhow you know. It will be given in the solvation of the problems. Sometimes it is given as 0.38 oersteds, the CGS units of BH value at horizontal field. Okay? And M is nothing but magnetic moment, 2 pi is constant, T is time period, please. So this is how you can compare between the electrostatics time period in electrostatics and also in magnetism. Clear? Any doubts regarding these formulas? Any doubts? So there you use I by P, of course, and here I by MBH. BH is magnetic field of Earth's horizontal magnetic field. Earth's horizontal magnetic field, please. Clear? So I think almost the comparison things are over regarding the electrostatics and magnetism. Now, let us, I think one more is left over, please. One more, last one. That is Gauss laws. Last one, last and final. Last comparison. That is electrostatics and magnetism. So already you have studied Gauss laws. What are Gauss laws here? Integral closed, okay, E dot dA is equal to 1 by epsilon naught times Q inside. Why? Because here negative charge, positive charge is existing in dipole. Okay? But what about Gauss laws here? Integral, if you put it in the place of EB, okay? In the place of E, what here? E dot dA. అదొద్దు మీకు E dot dA ఇక్కడ B dot dA. If you take here, what happened in magnetism? Minus M plus M does not will be there. Minus M plus M ఉండవు. Pole strength ఒకటే. అంటే అర్థం ఏంటంటే even if you cut the magnet into smallest piece, the piece will be having north and south pole existing. North pole వేరేగా south pole వేరేగా ఉండదు. అంటే మైనస్ M ప్లస్ M ఇక్కడ ఉండవు. So monopoles does not exist here in the magnetism. Monopoles, as like here minus q plus q existing, here monopoles does not exist. Does not exist. Therefore, what is the net flux, magnetic flux? Zero. So here Gauss laws are not so famous. Integral B dot A, B dot dA is equal to 0 because here monopoles ఉండవు. నార్త్ పోల్ వేరేగా సౌత్ పోల్ ఉండవు. మ్యాగ్నెట్ ఎంత చిన్న ముక్క కట్ చేసినా నార్త్ సౌత్ ఉంటాయి ఇక్కడ. అండ్ హియర్ మైనస్ ఎమ్ ప్లస్ ఎమ్ ఉండవు, రెండు ఒకటే వాల్యూ ఎమ్. సో ద నెట్ మ్యాగ్నెటిక్ మూమెంట్ ఎంత అవుతుంది? 0 అయిపోతుంది. దేర్ ఫోర్ ఇంటిగ్రల్ బి డాట్ డిఏ 0 హియర్. ఇంటిగ్రల్ బి డాట్ ఏ 0 అండ్ హియర్ ఈ డాట్ డిఏ ఈజ్ ఈక్వల్ టు క్యూ ఇన్సైడ్ బై ఎప్సిలాన్ నాట్. సో దీస్ ఆర్ ద comparison of Gauss laws in electrostatics and in magnetism, please. Clear? Right. So this is the main comparison in this chapter. Now we are entering into the actual thing. That is Earth's magnetism. Okay? Very interesting topic now. Earth's magnetism. Okay, we will be studying little geography about the Earth. So if you see, this is the structure of the Earth. And these are geographic North Pole. And this is geographic South Pole. Geographic North Pole of the Earth, geographic South Pole of the Earth. And this is the equator, of course. Okay? This is the geographical equator of Earth. That's the point. If you see that, and we all know Earth is rotating from west to east, running from north to south. That is already I told you in gravitation chapter. Okay, na? Right. Now we have to know some terms, that is dip, declination, all those terms we have to understand now in this Earth's magnetism. Last topic in this magnetism matter. Suppose if you take some magnetic compass needle. Suppose if you take a magnetic compass needle. Suppose take some magnetic needle or compass, put it over anywhere on the Earth's surface. So what it will do is, the North Pole will show down and South Pole will show up. Take a magnetic compass, put it anywhere, North Pole is showing down, South Pole upward. What does it mean? నార్త్ కిందకి చూపిస్తుందంటే అర్థం ఏంటి అంటే ఎర్త్ లోపల ఎవరైనా సౌత్ పోల్ ఉందా? యూ విల్ బి అస్యూమింగ్ అది ఇమాజినరీ. అంటే ఇన్సైడ్ సంబడి ఈస్ పుల్లింగ్, దట్ మీన్స్ సమ్ ఇమాజినరీ మ్యాగ్నెట్ ఈస్ దేర్ ఇన్సైడ్. యూ హెవ్ టు అస్యూమ్ లైక్ దట్. సో వాట్ ఐ విల్ డూ ఈస్ ఐ విల్ టేక్ సమ్ ఇమాజినరీ మ్యాగ్నెట్ ఇన్సైడ్ ద ఎర్త్. దిస్ ఈస్ నాట్ రియల్ ప్లేస్, ఇట్ ఈస్ imaginary magnet. I am writing here imaginary magnet. See, please make it, this is not real magnet, it is imaginary. Why I am taking imaginary? Because when you put the compass here, north is coming down. That means what? Somebody is there inside south. So appudu idu enta avutundi? South pole. And same compass when you put it here, it will be showing as south here and north. So what does it mean? Somebody is inside North Pole. That is imaginary north. So with this it is very clear that this is magnetic North Pole of the Earth and this is magnetic South Pole of the Earth. Please make a note, this concept is very very important. Geography. When you take the compass and put it, North Pole is showing downwards. Okay? And here South Pole. That means what does it mean? Inside somebody is there pulling. Imaginary person. That is, we are assuming as imaginary magnet. This is imaginary magnet. Not real. So now suppose if you draw lines according to the concept, what happens? From north the lines are going. You can see. Imaginary lines, magnetic lines. So here what happens? Even though you are assuming ఇక్కడ North Pole అనుకున్నా, ఇది మ్యాగ్నెటిక్ సౌత్. సో ద లైన్స్ ఇక్కడ డాక్యుమెంటేషన్ ఏంటి, లైన్స్ ఆర్, even though you are assuming imaginary north here, lines are coming from magnetic south of the earth towards magnetic north. If you observe carefully from the imaginary north and south, if you draw lines here, see here, if you draw lines, magnetic lines of forces, but here lines are coming from magnetic south pole. It is documented, real. This is not real, it's imaginary. So magnetic south pole nunchi magnetic north pole of the earth ki veltunnayi lines. Okay, and this is horizontal. You can see maximum this is horizontal, earth's horizontal field. Vertical is very less. Clear? Very very important thing here. And you can see with this it is very clear. For example, if you take any magnetic compass, put it anywhere, somewhere over here. Then, see here, if you take a magnetic compass and put somewhere over here, if that compass is making some angle with Earth's horizontal field, that is called as dip. Okay, it is indicated with the letter delta. If the magnetic compass is making some angle with Earth's horizontal field, then it is called as dip. Compass needle, if makes angle with Earth's horizontal field, that is called as a dip. And please you can observe one more thing here. So this is magnetic south అని చెప్పాను కదా మీకు, ఇమాజినరీ మ్యాగ్నెట్ తీసుకొని, దిస్ ఈజ్ మ్యాగ్నెటిక్ నార్త్, చూడండి ఇది ఇమాజినరీ ఇది. సో లోపల సౌత్ ఎక్కడ ఉందో, సో దిస్ ఈజ్ వాట్ హియర్, దిస్ ఈజ్ మ్యాగ్నెటిక్ నార్త్ పోల్, దిస్ ఈజ్ మ్యాగ్నెటిక్ సౌత్ పోల్. దట్ మీన్స్ ఇఫ్ యూ అబ్జర్వ్ కేర్ఫుల్లీ, దిస్ టిల్ట్ ఈజ్ అరౌండ్ 11.2 to 11.3 degrees with the geographic north pole and magnetic north pole of the earth. Magnetic north pole ki geographic north pole tilt and angle 11.3 degrees, nearly 11.2 to 11.3 degrees, please. This was the tilt observed. ఎందుకంటే ఇదంతా ఇమాజినరీ, మ్యాగ్నెట్ నిజంగా లోపల లేదు. యూ హావ్ అస్యూమ్డ్ బికాస్ కాంపాస్ is showing downward north, that means south is here. Compass is showing south, north is there. So field lines are coming from magnetic south to magnetic north. So between these magnetic north of the earth and geographical north, the tilt angle is around 11.2 to 11.3 degrees. So dip ఏంటి, ఇప్పుడు ఇక్కడ ఎక్కడైనా కాంపాస్ పెడితే, if suppose that compass is making some angle with the horizontal, earth's horizontal field, that is called as dip. Clear? Please write down. Very very important concept అండి ఇది. కాన్సెప్ట్ వస్తేనే మీకు ఎగ్జామినేషన్లో బిట్స్ మీరు ఆన్సర్ చేయగలరు. ఓకే, you can answer bit questions, otherwise you can't, please. Understanding the point here? Clear? So this point is very 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 important. You can see, if you take the compass, shall I draw here or there on, I'll show. Okay, you can see here, this compass, this is vertical component, this is horizontal component of earth, this is vertical component of the earth. I am showing here compass. This is the compass, magnetic compass. This is the line I have shown there. This is the line, field line. Okay, you can see at this point, this is vertical component of the earth's horizontal field, vertical component of the field of the earth, and this is BH. And this angle will be called as delta, dip angle. Adotna, if the compass, if you put out on the magnetic, earth's field here, which is coming from south to north, you can see magnetic south of the earth to magnetic north of the earth. అక్కడ ఈ కాంపాసు ఎర్త్ హారిజాంటల్ ఫీల్డ్తో ఏదైతే యాంగిల్ చేస్తుందో, దట్ ఈస్ కాల్డ్ యాజ్ డెల్టా డిప్. dip. This is vertical component of the earth field. This is the horizontal component of the earth field. BH and BV. Okay. Now you can see this is the, I'll draw once again. This is the compass, north south. This is earth's horizontal field. This is the magnetic field of the earth. What is this one? Magnetic field of the earth. And this is the vertical component. This is horizontal component of earth. So this is the angle, delta. Okay. So from here you can observe carefully. If this is delta, this is also delta. So what is tan delta here? Tan theta or tan delta? Opposite by adjacent. Opposite. You can see opposite. You draw the line. Opposite by adjacent. BV by BH. Okay. BV అంటే ఇక్కడ అంటే ఎర్త్స్ వెర్టికల్ కాంపోనెంట్, BH అంటే ఎర్త్స్ హారిజాంటల్ ఫీల్డ్. ఎర్త్స్ వెర్టికల్ కాంపోనెంట్, ఇది ఎర్త్స్ హారిజాంటల్. That is tan delta. And what are the components of this earth's magnetic field? Okay. ఇది ఈ డైరెక్షన్ యాక్ట్ అవుతుంది, ఇది theta. So what is this one? BE. What is the component? Horizontal component is given by BE cos delta. You can see BE cos delta. This, what is BE actually? Earth's horizontal field and you can see the direction. And what is here? B vertical. B vertical is nothing but BE sin delta. So from this you can get tan delta is equal to BV by BH. Or else you can also get squaring both sides. Squaring both sides. What happens now? BV square plus BH square under root is equal to BE. Another important formula. Because sin square delta plus cos square is 1 అయిపోతుంది కాబట్టి ఇక్కడ BE square whole square into 1 under root. So BE, that is Earth's horizontal field, is equal to root over BV square plus BH square. Okay, that is what are BV and BH? Horizontal component of the earth field, vertical component of the earth field here. That means because we are putting the compass on the magnetic field, wherever you ekkada తీసుకున్నా సరే అక్కడ you can see the magnetic field compass, the field is making some angle with the earth's horizontal. Earth's horizontal the angle చేస్తుంది, and that you are calling as dip. Okay, that you are calling as dip. Clear? Any doubts? Note down these formulas. Very, very important, please. BE cos delta and BE sin delta, horizontal and vertical components, values. Clear? Any doubts regarding the concept? Right. Now let us try to understand after this one. Two more points are there. Let us define some more points. This is geographical equator. Okay. Now already define this angle. that is making an angle of 11.2 to 11.3 degrees tilt between the magnetic north of the earth and geographical north pole. Suppose if a plane is passing through the geographical north pole. Suppose a plane passing through the geographical north pole, and that is called as geographic meridian. That is called as geographical meridian. A plane passing through the geographical poles, geographical north pole and geographical south pole, that is called as what? Geographical meridian. In the same way, a plane passing through magnetic poles of the earth called as magnetic meridian. And if you observe carefully, there will be small tilt between these two meridians. That angle is called as declination. Because suppose this is magnetic meridian and this is geographic meridian. And geographic meridian ante a plane passing through geographical poles of the earth is geographical meridian. A plane passing through the magnetic poles of the earth, and a magnetic north pole, magnetic south pole, that is magnetic meridian. Both are making some angle. That D is called as declination. Very, very important. That D is called angle between the geographic meridian and magnetic meridian, please. Okay? And please make a note, ఈ magnetic meridian ఏదైతే మీరు అనుకున్నారో, always if the compass is in this way, in this meridian, that dip is called as true dip. That is called as true dip. True dip delta. అంటే maximum ఎక్కువగా compass makes an angle with the horizontal, okay, in the magnetic meridian only. Magnetic meridian ఏంటి? Plane passing through the magnetic axis of the earth. అంటే ఇగో మ్యాగ్నెటిక్ యాక్సిస్ ఏంటి? మ్యాగ్నెటిక్ నార్త్ పోల్, మ్యాగ్నెటిక్ సౌత్ పోల్. అందులోంచి పాస్ అవుతున్నప్పుడు మ్యాక్సిమం నీడిల్ అక్కడే ఉంటుంది. అలాంటి డిప్ని మనం ట్రూ డిప్ అంటాం. అలా కాకుండా ఫర్ ఎగ్జాంపుల్ ద మ్యాగ్నెటిక్ కాంపాస్ ఈజ్ ఇన్ సమ్ అదర్ ప్లేన్ అదర్ దెన్ మ్యాగ్నెటిక్ మెరిడియన్, దట్ ఈస్ కాల్డ్ యాజ్ అపారెంట్ డిప్. దట్ ఈస్ కాల్డ్ యాజ్ అపారెంట్ డిప్ యాజ్ డెల్ డాష్ ఆర్ డెల్టా డాష్. మీకు అర్థమవుతుందా? ట్రూ డిప్కి అపారెంట్ డిప్కి తేడా ఏంటి? ట్రూ డిప్ అంటే మ్యాగ్నెటిక్ మెరిడియన్, అంటే మ్యాగ్నెటిక్ మెరిడియన్లో నీకు కాంపాస్ ఉంది. ఫర్ ఎగ్జాంపుల్ ఇదిగోండి కాంపాస్, దిస్ ఈస్ ద కాంపాస్ and this is the horizontal component and this is the vertical component of the earth. Suppose this is the horizontal component. Suppose if this is the angle delta, చూడండి కదా, compass is making angle with the horizontal of the earth, and in which is this one magnetic meridian లో ఉంది. So this is true dip. This is true dip. If suppose this is in some other plane, somewhere here, and it is making some angle with that horizontal, that is called as apparent dip. Now I'll explain that also. One formula is there, very very important. Please try to understand. So you can see here, this is delta, and these two are making some angles. Geographic meridian, magnetic meridian, and this is horizontal. Then what is this one? You can see this is BH. So ఇది ఎంత అవుతుంది అప్పుడు? BH cos. అదవుతుందా? So you can see this one BH kada, BH cos theta అవుతుంది. So like that you can analyze the concept here. Like that you can analyze the concept. Any doubts regarding this one? Okay? Right. Now one more point I'll discuss for you. True dip చెప్పాను కదా, apparent dip I'll try to explain now. Apparent dip, for example, suppose, okay, now let us take this one, okay, see in this figure, this one magnetic meridian is here, this is mm, this is magnetic meridian. యాక్చువల్లీ ఈ మెరిడియన్లో మనకి కాంపాస్ ఉండాలి, కానీ ఇప్పుడు ఏం జరిగింది చూడండి, ఇది మ్యాగ్నెటిక్ మెరిడియన్, ఇదేమో ఎర్త్ హారిజాంటల్ ఫీల్డ్. చెప్పాను కదా మీకు, ఐ టోల్ యూ always the compass, if it is in magnetic meridian, that is a plane passing through the magnetic axis, then it is true dip. అలా కాదు, ఇప్పుడు ఇది వేరే ప్లేన్, అనదర్ ప్లేన్, దిస్ ఈజ్ అనదర్ ప్లేన్ ప్లీజ్, నాట్ మ్యాగ్నెటిక్, అనదర్ ప్లేన్. ఈ ప్లేన్లో ఫర్ ఎగ్జాంపుల్ ఇఫ్ ద కాంపాస్ ఈజ్ దేర్, okay, and suppose you can take some angle also, that one has some alpha. Suppose this is angle alpha, and is some other plane making some alpha with the magnetic meridian. Now if this is alpha, what is this one? What is it? Alpha kada idi, angle pakkadi. What is it? BH cos alpha. BH cos alpha, adjacent by hypotenuse. Now suppose if this compass is making some del, which is called as del dash, that is called as apparent dip, because this is another plane. This del dash is called as apparent dip, because this angle compass is not making in the magnetic meridian, some other plane, and this plane making an angle alpha with this one, horizontal. Okay, so ఇది horizontal BH కాబట్టి ఇది alpha అయినప్పుడు ఇది ఎంత అవుతుంది? BH cos alpha. BH cos alpha. And this is of course the vertical plane BV. Now from this you can calculate the tan del dash. Tan theta, what is tan theta? Opposite by adjacent. BV by adjacent, that is BH cos alpha. So this is how the apparent dip is calculated. So tan del dash is equal to BV by BH cos alpha. Clear? So this is the main difference between true dip and apparent dip. Clear? Very good. Now I will derive the last one. In this one, very important. They are asking in the examination. Complete concept is explained for you very clearly to understand regarding various points of the Earth's magnetism. Okay? Now you have known the difference between true dip and apparent dip. Tera telisindi kada meeku. True dip and enti? What is true dip? If the compass is making some angle in the magnetic meridian with the Earth's horizontal field, that is true dip. If the compass is making angle in some other plane, then it is called as apparent dip. Just now you have seen. Now next case, for example, see, suppose this is say magnetic meridian. That means plane passing through the magnetic axis. Okay? Magnetic axis చెప్పాను కదా, magnetic north, magnetic south. Okay. Now దీనికి suppose there are two planes, for example say there are two planes. One is like this and another is like this. You can see these are the two planes making an angle 90 degrees here. You can see this is plane 1, this is plane 2. Here the question is two planes, separate planes. This is magnetic meridian, plane passing through the magnetic axis of the earth. ఈ రెండు planes ఉన్నాయి, of course, okay, and this is the magnetic meridian, this is the earth's horizontal field and this is earth's vertical component, horizontal vertical. Now suppose ఇది యాంగిల్ మనకి 90 ఇచ్చాడు, అంటే ఆ రెండు ప్లేన్స్ మధ్య యాంగిల్ 90 అనుకున్నారు. Suppose this angle is say some theta. Let us assume some angle theta or alpha. Okay na? Suppose if this is theta, what happened to this angle now? 90 minus theta. Let us assume this plane making with the horizontal theta, ఇదంతా 90 minus theta అవుతుంది. Now what about this component? ఇది theta కదా, అప్పుడు ఇది ఎంత అవుతుంది? BH cos theta. And what about this component? ఈ కాంపోనెంట్ యాంగిల్ ఇక్కడ ఉంది, ఓకే, ఇది BH. So this will become BH cos 90 minus theta, which is nothing but BH cos 90 minus theta, first quadrant, sin theta. So BH sin theta. So these are the two planes. Now let del be the true dip, which is in magnetic meridian compass. Okay. Let del dash in first plane. Okay, del 1 and పెట్టుకుందాం, del 1 and del 2. Del 1 and del 2 are the dips in first plane, del 1 and del 2 second plane dips. ఇది ట్రూ డిప్, ఇవి అపెరెంట్ డిప్స్, ఈ రెండుని వేరే దాంట్లో ఉన్నాయి అపెరెంట్ డిప్స్. Now we'll get a relation between del 1 and del 2. Okay, so in magnetic meridian లో మనకి ఏంటి ఫార్ములా? tan del is equal to what? V, vertical component by horizontal component, equation 1. Okay na? Vertical component by horizontal. And in first plane ఎంత అవుతుంది? tan del 1 is equal to opposite by first plane adjacent, that is BH cos theta, equation 2. In second plane tan del 2 is equal to opposite by adjacent, that is BH cos 90 minus BH sin theta, equation 3. Now observe carefully this equation. What we'll do is this one, from this separate sin theta and cos theta. Okay, so in equation 2, what is cos theta? In equation 2 cos theta ఎంత అవుతుంది? BV by BH, that's horizontal vertical, tan del 1 కిందకి వచ్చేస్తుంది. అలాగే ఈక్వేషన్ లోని మూడో ఈక్వేషన్ sin theta ఎంత అవుతుంది? వాట్ ఇస్ sin theta? BV by BH tan del 2. Now what I'll do, squaring both sides and adding. Squaring both sides and adding. ఏమవుతుంది అప్పుడు ఇది sin square theta plus cos square theta 1 అవుతుంది లెఫ్ట్ సైడ్ ఫ్రమ్ ట్రిగ్నోమెట్రీ. ఈ రెండు ఏమవుతుంది ఒకసారి చూద్దాం. BV square by BH square 1 by tan theta cot theta పైకి వెళ్ళిపోతుంది. సో ఇది cot square del 1 plus again this one BV square by BH square 1 by tan theta again cot. So పైకి వెళ్ళిపోయి cot square del 2. Now here what I'll do, I'll take common BV square by BH square into bracket cot square del 1 plus cot square del 2. Now see the equation 1. ఈ ఈక్వేషన్ 1 లో మీరు చూసినట్టు దీన్ని స్క్వేరింగ్ చేయండి. స్క్వేరింగ్ ఏమవుతుంది? tan square del is equal to BV square by BH square లేదా 1 by tan square del is equal to BH square by BV square. చెక్ చేసుకోండి. BV BH tan. బట్ 1 by tan square ఎంత అవుతుంది? del cot square del is equal to BH square by BV square. Put that one, copy paste here. So 1 is equal to cross multiply చేసాం. క్రాస్ మల్టిప్లై చేయండి. క్రాస్ మల్టిప్లై చేస్తే ఇందులోంచి ఇది ఇక్కడికి వచ్చేస్తుంది. BH square by BV square is equal to cot square del 1 plus cot square del 2. But what is BH square by BV square? Cot square del. So cot square del is equal to cot square del 1 plus cot square del 2. So this relation is very, very, very important when two planes are perpendicular to each other and it is making some angle with the Earth's horizontal field. Very, very important. I am telling you, true dip, apparent dip మధ్యన difference తెలుసుకోండి. True dip means when the magnetic compass resultant makes angle with the horizontal in magnetic meridian only. Always in magnetic meridian. Magnetic meridian అంటే plane passing through the magnetic axis. Magnetic north and magnetic south. ఆ యాంగిల్ ట్రూ డిప్ అండి. అలా కాకుండా if that compass is some other plane and the net magnetic moment, the compass if it is making some angle, then it is called apparent dip. ట్రూ డిప్ ఎప్పుడు కూడా మ్యాగ్నెటిక్ మెరిడియన్లో ఉంటుంది. మ్యాగ్నెటిక్ మెరిడియన్ అంటే ప్లేన్ పాసింగ్ టు ద మ్యాగ్నెటిక్ యాక్సిస్ అండ్ ద కాంపాస్ మేకింగ్ యాంగిల్ విత్ ద ఎర్త్స్ హారిజాంటల్. ఆల్వేస్ కాంపాస్ మేక్స్ విత్ ద ఎర్త్స్ హారిజాంటల్. Please make a note. This is very, very important regarding the examination point of view. Okay, clear? Now let us see the next one. Tangent galvanometer, please. Clear? Next, tangent galvanometer అంటే చూద్దాం. Let us see what is meant by tangent galvanometer. See, a few points are left over. A few points. Tangent galvanometer generally you will be having in your physics laboratory. Generally in your physics lab you are having. So it will be having like this in this phase. Tangent galvanometer ఈ విధంగా ఉంటుంది అంటే ఒక కాయిల్. And here one compass will be there, aluminum pointer. Readings will be there from 00, 90 degrees, 90 degrees, 00. And graduations will be from 0 to 90, 90 to 0, 0 to 90 and 90 to 0. Okay, it will be in this direction like this. ఈ ఫ్యాషన్ ఉంటుంది. And it will be like a tripod. And here some coils will be there for connecting the number of turns. General figure ఉంటుంది. So what is the main function? For example, current is flowing. Assume current is flowing in the coil. So when current is flowing, I told you by using right hand curl rule. By using right hand curl rule, what is the magnetic field direction? Inside. So magnetic field will be inside. So this is the direction of magnetic field. By using right hand curl rule, inside magnetic field. Suppose this is center with radius r. So what is the magnetic field at the center? Field at the center is given by mu naught I by 2r. If number of turns are there n, so mu naught I by 2r into n is the magnetic field due to this coil. Magnetic field due to this coil. And you know this is the field direction of the earth. This is the field direction of the earth. BH. So observe carefully, one is acting like this, one is acting like this. So this is the resultant field. Okay, this is the resultant. One is acting in this fashion and one is like this. So this is the resultant. So what is tan theta here? Opposite by adjacent. Opposite and enta? This value B. Opposite by adjacent, or you can write B is equal to BH tan theta. This B is due to the coil. Mu naught I by 2R into N is equal to BH into tan theta. So from this, if you find out what is I is equal to BH tan theta multiply with the 2R, okay, by mu naught N. If you observe carefully, BH, mu naught, N, 2 are all constants. Therefore, I is equal to K into tan theta, or I proportional to tan theta. So, in tangent galvanometer, the current flowing is directly proportional to the tangent angle. Okay? That because all these are constant, you can see. Mu naught I, N, 2R, ఇవన్నీ కూడా స్థిరాంకాలు ఇవన్నీ. Constant కాబట్టి అక్కడ mu naught, 2R, we can see. Mu naught 4.10 per minus 2R. All these are constants here. So when you put constant K, I is proportional to tan theta. Clear? So this is the basic principle in the tangent galvanometer. Generally you will be doing in physics laboratory as an experiment. Okay? In moving coil galvanometer, I is proportional to theta. Ikkademo I proportional to tan theta. That is the major difference. Ikkada I proportional to tan theta, I proportional to theta. Adi renditliki difference. Okay? Now we'll see the next item, that is vibration magnetometer. Vibration magnetometer. Now generally what is the main vibration magnetometer and enti? Generally ఇది కూడా physics lab లో ఉంటది. It is a box like structure. Two glasses will be there. Inside one, with the help of a thread, magnet is suspended and suspended in the magnetic field. That magnet, what happens is, it will be oscillating. Field lo suspend చేసినప్పుడు magnetic field లో it is suspended with the help of a thread and magnet. So magnet torque punches, it will be making small simple harmonic motion. So from that you can calculate what is the time period 2 pi into I by MBH, where I already told you moment of inertia of the magnet, which is ml square by 12 about the axis, because it is making like this simple harmonic motion in the field. M magnetic moment BH is the Earth's horizontal field given. T is time period. So here if 2 pi is constant, for a given magnet I is also constant, same value, unless until you change. Moment is also constant. So T is inversely proportional to root field. So a relation of form and T root BH is equal to constant, or T1 root BH1 is equal to T2 root BH2. Like that you can find the value of Earth's horizontal field at different places. So what are the main uses of vibration magnetometer? By using this, you can find the time period. You can find the Earth's horizontal fields at different points, at different places. You can compare magnetic moments of two given bar magnets, whose values are M1 and M2. Rendu bar magnets meeku ichinapudu, you can compare the time period by this experiment by using the formula 2 pi root over I by MBH. Okay? So like this, these are the main uses of vibration magnetometer. You can find the time period, you can compare the magnetic moments by some method or difference method. చూడండి ఎందుకని అన్నానంటే some method అంటే అర్థం ఏంటి? ఫర్ ఎగ్జాంపుల్ see, magnets are like this, south north, south north. సో మొమెంట్ ఇటువైపు ఉంటుంది M1, ఇది కూడా మొమెంట్ M2. సో both are in same direction. This is what? M net is equal to what? Sum of those. Suppose the magnets are in this fashion, south north and south north. So from this one direction M1 magnetic moment, and from this magnetic moment is in other direction. So the resultant is what? M1 minus M2, M net is equal to. So this is difference method. Like this also you can compare the magnetic moments, some method and difference method, and thereby you can compare the time periods. Okay, so like this you can utilize the vibration magnetometer, and the main principle is when it is suspended freely in the field, magnetic field, the bar magnets make simple harmonic motion in the main position. That is the main principle of the vibration magnetometer. The bar magnet, if it is suspended, it makes simple harmonic motion in the main position, please. Okay, and next one, last points are there left over. Okay, what is intensity of magnetization? Intensity of magnetization. Intensity of magnetization ante enti? See, generally intensity of magnetization is indicated by the letter capital I. It is internal, not external. See, intensity of magnetization I is given by ratio of magnetic moment per unit volume. Intensity of the magnetization given by ratio of magnetic moment per unit volume, ante ampere meter square per meter cube. Meter square cancel. So what is the unit? SI unit ampere per meter. Intensity of magnetization is given unit enti ampere per meter. It is a ratio of magnetic moment per unit volume. Intensity of magnetization. It is internal. It is internal. And next one we can also discuss about H. Magnetizing field intensity. Magnetizing field intensity H. This is external. Okay. So ఇది ఎలా ఉంటుందని చూడండి రిలేషన్. I is directly proportional to H, or I is equal to some constant into H, or I is equal to some psi into H. This is called as psi, or whatever you can call it as zeta or psi. It is a constant. Okay, and it is dimensionless because it is the ratio of I by H. Because it is the ratio of intensity to that of magnetic field, magnetizing field intensity. Rendu intensity kabatti it doesn't have any units and dimension. It will be having some value. So I by H is equal to zeta. ఇప్పుడే చెప్పాను మీకు ఏంటి, I depends upon H, more intensity, internal. This is external. Less H, less this I value. So I can take B directly proportional to as H plus I, external and this is internal, or B is equal to some constant into H plus I, or B is equal to mu naught into H plus I, or I can write magnetic field is equal to induction is equal to mu naught into H plus psi H, because I just know I is equal to psi H. So ఇక్కడ కామన్ తీస్తే B is equal to mu naught into H కామన్ తీసేద్దాం, 1 plus psi into H. So these formulas are very important in explaining the properties of magnets. Okay, so B is equal to mu naught into 1 plus psi into H. Very important one. Mu naught into 1 plus psi into H. Okay, any doubt? So this one, what here you can even change the formulas when and as and when required depending upon the medium. If vacuum, the formula will be one thing. If any medium will be there, formula will be changing. Okay, for example, no medium is there, no medium, vacuum, no medium, vacuum, then you can write B naught is equal to mu naught into H. B naught is equal to mu naught into H. Okay, no medium, vacuum. B naught is equal to mu naught మీకు కనుక తెలుసు, permeability of free space. Okay, 4.10 per minus Henry per. This is external field, magnetizing field intensity. Okay, and I is internal. It depends upon H only, please. Proportional to H, and zeta or psi is the constant there. It is a dimensionless and unitless quantity. Okay, ఎటువంటి యూనిట్స్ ఉన్నాయి ఎందుకంటే రెండు ఇంటెన్సిటీ కాబట్టి రేషియో క్యాన్సిల్ అయిపోతుంది. ఓకే, సపోజ్ ఎనీ మీడియం ఇచ్చారు, అప్పుడు ఈ ఫార్ములా ఎలా మారుతుంది చూడండి. ఇఫ్ ఎనీ మీడియం ఇస్ దేర్, అర్థమే కదా పాయింట్స్ మీకు. ఇంటెన్సిటీ ఆఫ్ మ్యాగ్నటైజేషన్ అండ్ మ్యాగ్నెటిక్ ఫీల్డ్ magnetizing field intensity and magnetizing field intensity. You have to understand the literature here, terms. This letter, this psi, is also called as magnetic susceptibility. Susceptibility. It varies with ferro, para and diamagnetic substances values. So this psi or zeta is called as susceptibility, magnetic susceptibility. It is the ratio of intensity of magnetization to that of magnetizing field intensity. Now for any medium, how the formula change we will see. For no medium you have seen B naught is equal to mu naught H. For any other medium, we'll see what happens. For any other medium, Bm can be written as mu naught into 1 plus psi into H. Bm is equal to mu naught into 1 plus psi into H, or simply you can write as any other medium, magnetic field is equal to this mu naught will be changing into mu m into H. Please make a note here. Very, very important this one. Mu m into H. అంటే ఈ వాల్యూ అంతా మారిపోయింది మనకి. mu naught into 1 plus zeta or psi is becoming what? Mu m. Mu naught into 1 plus zeta is becoming mu m. And we also know another formula, relative permeability is equal to mu by mu naught or medium mu. Permeability of the medium by permeability of free space. Mu m. This formula is also we will be using regularly. Relative also we are using electrostatics also. Epsilon naught is equal to epsilon m by epsilon naught. So mu r can be also written as mu m by mu naught. Okay. And this finally you can write it as, clear? Yes. So these formulas are very, very important. In no medium, in vacuum, B naught is equal to mu naught H. In vacuum, in any medium, Bm is equal to mu m H. Bm is equal to mu m into H, please. Clear? Adotha points ikkada. These are very, very important formulas. Now we are coming to the last point and magnetic susceptibility value for different particles. Magnetic susceptibility values for different. Ippude cheppanu kada, what is magnetic susceptibility? It is the ratio of intensity of magnetization to the magnetizing field intensity. So ratio kabatti for ferromagnetic substances, ferro and iron, cobalt, nickel, steel. Okay, these are strongly attracted by the magnetic particles. Ferro and ferromagnetic substance and strongly attraction by the magnetic particles like iron, cobalt, nickel, steel. These are the examples for ferro. Okay, in ferromagnetic substances, the susceptibility psi or zeta is very much large, very large value, around thousands. 10 power 3 you can see is having a very large value and is positive value. Very large value and is a positive around 10 cube for ferromagnetic substances. And for paramagnetic substances, para and like aluminium, manganese, etc. These are feebly attracted by the magnetic particles. Examples enti aluminium, manganese. So ikkada zeta value or psi value is around 2.3 in 10 power minus 5. Okay, 2.3 around 2.3 in 10 power minus with positive value. You can see here getting negative value. 10 power minus 5 and kinda 5 and still lesser value. Negative kaadu. Deeni meeda idi chala ekkuva, idi takkuva. 2.3 into 10 power minus 5 and kinda 10 power 5. So around 0.000 something will be getting for para. And lastly for dia. What are diamagnetic substances? Strongly repelled by the magnetic substance. Strongly repelled. What are diamagnetic substances? Strongly repelled like copper, antimony, bismuth. Copper, antimony, bismuth. Okay? These are some examples for diamagnetic substances and copper, antimony and bismuth, strongly repelled. And this value is zeta is almost very negative value and it is minus 10 to the power of minus 5. Okay, this is 2 points in 10 power minus 5. And the positive value, very large value for zeta, that is psi, is for ferro. Okay, examples already I told you: iron, cobalt, nickel, steel, etc. Para, aluminum, manganese, dia, copper, antimony, bismuth. Sometimes hydrogen gas is also taken as diamagnetic substances. So here the value is negative value, minus 10 to the power of minus 5. Clear? And last point, Curie's temperature. This is the last and final one. What is Curie's temperature? See, as you increase the temperature, what happens? At certain temperature, ferromagnetic substance is converted into paramagnetic substances. That temperature is called as Curie's temperature. Curie's temperature, scientist. Okay? Curie. So, a temperature vaddate ferro is converted into para. At what temperature? Ferro is converted into paramagnetic substances. Paramagnetic substances. That temperature is called as Curie's temperature, which is indicated with Tc. Okay? If I write T, it is absolute temperature. It is absolute, that is Kelvin temperature. Tc is Curie's temperature. And we have an example for iron. Iron, the Curie's temperature is around, I think, 770 degrees centigrade. Okay? For iron, the Curie's temperature is 770 degrees centigrade. So, a temperature vaddaithe ferromagnetic substance is converted into para. That temperature is called as Curie's temperature. Okay, Tc. Clear? Okay. And we have a formula also, one more. Zeta or psi inversely proportional to 1 by T minus Tc. T is absolute temperature, Tc Curie temperature, and this one is magnetic susceptibility, inversely proportional to temperature. That is Curie's temperature or absolute temperature. Okay, where ferro is converted into paramagnetic substances. And suppose when the temperature is increased above Curie's temperature, okay, above the Curie's temperature can inka penchite, we can use this relation. Temperature above Curie's temperature, increasing temperature above Curie's temperature. Okay, then zeta or psi is inversely proportional to 1 by T minus Tc. In that case, you will be using this formula. This is absolute temperature, this is Curie's temperature. Clear? So, this chapter, magnetism matter, is nothing but one short chapter. I told you it's a very easy chapter, and scoring in MSET you will be getting around 1 to 2 marks. Okay? And this is end of the chapter. Please study well the concept given by me regarding dip declination, and so many things we have discussed regarding Earth's magnetism. Please study well. In that, problems also coming. Again, we will be meeting in the next chapter.